Okay. So now we will study the, not the digital, the data. So now we'll study the block cipher in a more structured way. Remember that we mentioned before we go to, like what we did in the previous chapter was mainly symmetric cipher approaches. We didn't really look at whether it's block or stream. Remember I said there are two ways to encrypt. One called stream cipher, which means that your message is coming one word after the other, and your key is also flowing and applied directly on the message one by one as they go through, okay? This is called stream cipher. The other approach, which is block cipher, by the way, the slides here will discuss these differences also in more details, is not this way. It's actually you take a few messages, you compose one block, and then you take a key applied to the whole block. And then this will generate a block of cipher. You transmit that. Then you take another group of messages, which is one block of a fixed size. You apply the key to the whole block. You end up with a block of cipher. You send that and so on. Okay. Mainly, what are the differences between those two in terms of practicality and implementation and so on is going to come through those slides. Our focus from now on until we finish, so when we talk about DES, even when we give a hint about AES, or when we discuss the other method, the asymmetric method of encryption, right? In both cases, that one is called the RSA, the standardized method there is called the RSA. In all these cases, we are going to talk about block cipher. Why? Because practically it's easier, and encryption-wise, it is stronger. We will see why, okay? We'll see why in a qualitative way, not a quantitative way, okay? So, a stream cipher, as I mentioned, this slide is give you just kind of examples and a little bit more explanation. I'm not gonna read it block by block, right? But it just talks about the fact that when you apply, which is explained in the next slide in a better way, in a couple of slides, okay? When you apply stream cipher, you are dealing with a flow of data, and accordingly, you have to manage the key in a slightly different way. I will explain that in one slide after this. For the block cipher, as I described it already, you deal with one block, and for each block, you can have your own key applied directly to that. And if you want to really achieve very high security, for each block, you generate a new key if you want to do that, okay? Here is the implementation of block cipher down here and stream cipher up there. Notice that in the stream cipher, what happens is, okay, data keeps going. This is transmitter side or encryption side. This is decryption side, okay? And as data is going, it's being ciphered by a particular key, and then you generate the ciphertext, which is being continuously transmitted to the receiver. And again, the receiver somehow have to keep up with the keys so that it can decrypt and generate the original message. Okay. Now, practically, this is not doable by generating a key for each element of that stream, because transferring that key to the receiver is going to be very difficult. So how do they do that? They typically have something called a bit generation stream for the key. So you have some algorithm which you feed it with some input, and then that algorithm, relying on that input, will continuously generate keys, okay? And if it's the same algorithm on both sides, transmitter and receiver, and if it is fed with the same input, then you can expect that over time, the keys generated here to encrypt the messages as they go one after the other are going to be exactly the same as the keys generated here to do the decryption of the messages one after the other. Is it clear? بمعنى, let's say that I feed that algorithm with a number. And what the algorithm is doing is simply, for example, taking the square of the value, right, which I feed at the input, and then multiplying that, for example, by the current time value. Okay. If the time here and here are exactly the same, so they are synchronized time, okay, then if I feed this input to this, it's going to generate keys here that is square of this value multiplied by time, right? Similarly, on the other side, square this value, which is exactly the same, multiplied by time. If the times are synchronized, then this is going to be exactly the same, right? Okay. So in the stream case, I have to have this called key stream generator algorithm. And that algorithm exists both at the transmitter and the receiver. Where is the key? The key is this seed or initial value that you feed to that algorithm, okay? So what I need to hide from my attackers is simply what's the initial value that I feed to my algorithm. Even though this is not what's used for the encryption, what's used for encryption are some keys generated from this system, okay? And the same, what's used for decryption are some keys, KI, K1, 2, 3, 4, and so on, generated from this system. But this is simply a function of this. So if I keep this hidden, then this also is hidden from an attacker, okay? But at the same time, this allows me to share that initial value only rather than sharing keys with every message, right? So what I do is I generate some initial key at the transmitter side. I find some backdoor secure way to share that with the receiver. And then for a large amount of messages, the transmitter and the receiver are going to use their generated keys to do the encryption and decryption. And they are going to be exactly the same because they use the same algorithm and they are initiated with the same key. And then after a while, of course, if I keep this forever, it's going to become unsecure. So after a large amount of messages, I'm going to do another initial value to reset these, right? Sorry. Okay. And then share that through some back secure communication with the receiver. And then we keep going through the stream, encrypting, decrypting without a need to share a key for each element of the stream. Clear for you? This approach might look practically nicer, but definitely slightly weaker. Mainly because eventually you end up with every message encrypted by a newly generated key, but that key is a deterministic function of the original key that you use here, right? Okay, so this means that the keys that you generate here are not independent from each other, right? The sub keys that comes out of here are not independent. They are simply a function of a same initial value. So they are not independent. K1, K2, K3 are not independent until you change the initial K. Right? In that case, you can generate some new values that are independent from the historic ones. Okay? But once this is fixed, all the generated ones here are keys. Remember the condition for Shannon says that the keys should be independent from each other and independent from the message. Right? Here, they are independent from the message, but they are not independent from each other. Okay? So that's slightly less secure. What about the block cipher? The block approach works completely different, right? Or different in a particular part, not completely, okay? In this case, remember what do? We collect a group of messages and then we feed a key to an encryption algorithm. So this is the group of messages, group of bits. Here, it was bit by bit if you deal at the bit level, okay? Here, it's a group of bits and then a key, which is another group of bits, and then using an encryption algorithm, whether it's substitution or transposition or a mix of both, right, to produce a group of cipher text bits. Okay. Now, the mapping from this to this relies on the key. Every time I have a new block, I should have a new key if I want to achieve perfect secrecy, and that's doable, but still at a lower rate. And every time I generate a new key, I have to also generate the same key on the other side, which means I have somehow to share it with the receiver side. From a security point of view, mapping a group of messages into another group of messages is a more secure approach. Because remember, at least earlier, we said that if you want to hide your messages protect your messages or cipher from a crypt analysis, don't do a one message to one message mapping. Don't do one letter to one letter. If you can do a group of letters to another group of letters, this makes it more difficult on a crypt analyst to figure out the statistics of your letters and map them to the original language statistics. Okay? Again, We will see more into this as we go further into the block cipher approaches. There are two important features that block cipher is trying to achieve. One of them is called diffusion, and the other one is called confusion. And we will see what they mean, how they are achieved when you do block cipher. Very difficult to do those when you are dealing with one message by one message mapping for the stream cipher. So that's why, generally speaking, from an implementation point of view, this is typically faster, right, to do block by block, and it's more secure, and that's why most of the practical ciphers that we use, except in very specific applications, most of the time we are using block cipher. And that's why we will focus on block cipher from now on until we finish the encryption methods, okay? Did I lose you, or are you still with me? I didn't do much yet. Anyways, just this slide, and I will stop. This slide shows you that very important thing. When we are doing group of messages to group of messages mapping, we can do any arbitrary mapping. So our mapping is not really that I take, for example, if my message was a B, let's say A bit, the guys who accredit your program, okay? If this was my message, right? Don't think of the fact that I do a group of message to a group of message similar to when we did this, right? For example, when we did only transposition, so something like this, okay? Because even though this is a group and a group, but it is not arbitrary. There is something maintained here. What's maintained in this case? The same letters are there, right? Reality is, when I do a group to group, when I do block cipher, I can do anything. I can map A, B, E, T to something like X, L, Y, Z, okay? And that mapping says that those four letters are always gonna produce those four letters. There is no association between a single letter and a single letter. Let me elaborate a little bit more into this example. Assume, for example, that now I want to map the word bin. You know, the past participle of be, verb to be, okay? If I want to map this, I will just pick. So ben, B-E-E-N, I'm gonna map those four letters to T, N, O, Q, right? Notice, I have the letter E here, and I have the letter E here, but none of those letters appear here, right? Because it's an arbitrarily 4 to 4. I will pick a particular 4 combination, and my key is gonna say that this 4 letters in this particular order are mapped into this 4 letters from the alphabet. There is no one-to-one relation at all. When I see bean, I'm gonna transmit TNOQ. Okay? Question for you. If I assume that, for example, my mapping is from like a block size of, okay, let me try to give this by a numeric example rather than by symbolic example. So if I am mapping from, if I have an alphabet which is composed only of the letters A, B, C, D, okay? So an alphabet which is composed only of 4 letters. And my block is gonna be 2 letters. So I can send any block of messages is gonna be 2 letters. So I can send, for example, AB or CB or AD or DA or whatever, okay? So it's only two blocks of letters, okay? Now, when I'm doing the mapping, okay, how many possibilities are there to map any 2 letters to any 2 letters?
We have only 2 possible options, and we have 26 letters.
Okay, and here we are not talking about, we are talking, I made it smaller. So we have only an alphabet composed of only 4 letters.
So 2 to the power of 4. So it's
2 to the power of 4. So we have I didn't get why 2 to the power 4?
We have two blocks, and we have four
Blocks of 2. تمام.
blocks of 2.
Okay, and you need to map them into blocks of 2 as well.
Okay.
طيب خليني okay. Let me make this simpler. Okay, so this is also a little bit more complicated. So assume that I have 4 bits. خلي الexample ده nice. Assume that I have 4 bits. تمام? And I need to map them to an arbitrarily outcome of 4 bits. تمام? So I need to map some input 4 bit at the input arbitrarily to some 4 bits at the output. In how many ways I can do this?
It will be one by one, not block of 2.
1 by 1.
Right?
لا ايه ال 1 by 1 مش فاهم.
كل رقم
Each one have 4 possibilities. 4 bits.
Okay. انا I want to map all the possible values خلي بالك. صح؟ يعني انا دلوقتي عندي 4 bits عايز اشوف كل ال possible values بتوعهم and then create a mapping that says this particular 4 bit combination is going to be this and this particular 4 bit combination is going to be this and so on. In how many ways you can do this? How do you figure it out? It's simply, you can think of this as,
I'm thinking about 4 power 2 minus 1 for each one.
ليه power 2?
4 power 2 because we have 16.
4 power 2 is 2 power 4 قصدك.
4
2 power 4 are the possible values for this. وبعدين
minus 1.
لا مش minus 1. مش minus 1. هو انت يعني مقربة من الانسر بس not as you said. It's quite different. بس الماينس 1 ليه رول كده هيجي دلوقتي. But we are not gonna subtract 1 and that's it. Okay. Again, when we do that mapping, we want for every possible value here to have some output cipher text here. تمام? For every possible values of the 4 bits at the input, we map it to a unique cipher output. It cannot be non-unique, right? Because in that case, it will not be impossible to decipher it, right? Okay. How many possible values here? 2 to the power 4 زي ما انت قلتي. صح؟ Okay. Now I need to map them to how many possible values الناحية التانية? 2 to the power 4, which means what? أول واحد, the first one of those, is gonna pick one of the 2 to the power 4, right? So the first one has a possibility of 2 to the power 4. Second one is gonna pick one from the 2 to the power 4 minus the one picked for the first one, because I cannot pick it again. It's unique. And then if you keep doing this, what's gonna be the result? 2 to the power 4 times 2 to the power 4 minus 1 times 2 to the power 4 minus 2 times 2 to the power 4 minus 3, which is gonna be what? Factorial of 2 to the power 4. Right? Now, if I have n bits, if I want to extend this to any number of bits, and I want to map them at the output to another set of n bits, what's going to be the value?
Factorial 2 power n.
Exactly. So it become 2 to the power n factorial. This is going to be the possible ways to do mapping from input to output. Right? Now, this means that if I want to transmit a key with this transmission system, how big is my key?
More than 2 to the power n.
Oh, actually 2 to the power n factorial. Right? Because if I want to send the key, what do I have to do? This has to map to this, and this has to map to this. How many mappings I need to send? 2 to the power n factorial, right? So my key length is going to be something in the size of 2 to the power n factorial. That's too much, right? So now we cannot just do arbitrarily mapping, which is, by the way, the most secure way to do it, but we cannot just do it. So what should we do? This will come inshallah in the next lecture. So how do they do? I just wanted to show you that block cipher has nice security because it has a very large key, but the problem of having that large key is that it's very difficult to transmit it to the receiver side. It's a big key, right? The size of the key is really large. So what should I do? I still need to transmit a small key, in the case of block cipher, but achieve a security equivalent to doing that arbitrarily 2 to the power n possibility mapping, because that one gives me really a nice protection. How they do that, we will discuss this inshallah in the next lecture. خلاص?